Hello students, let's continue with the interfacing. So let's see DAC interfacing with 8086 using 8255 peripheral interface device. So DAC, digital to analog converter. So there are many DAC chips available in the market, like 8-bit DAC chips, 12-bit and 16-bit chips are available. Let's discuss a DAC 0800, which is a 8-bit digital to analog converter IC. Okay, so this is the pin configuration of DAC 0800. So this is like we give digital input and get the analog output to this chip. If we give a digital input, we get the analog output. I out is the analog output current, which is to be converted to voltage to get the analog output voltage. Okay, so these are the input digital bits B1, B2, B3, B4, 4 bits here and 4 bits here. So these are the 8 input digital input. Okay, and I out is where we get the output current, analog current, and then I out bar is another output, like it is a complement of this. Okay, so the supply required is given V plus and V minus. Here is we give the supply, generally plus 5 volts or plus 12 volts is given here, and minus 12 volts is given here. Then this DAC requires reference voltage. Okay, so we give the reference voltage V reference positive at 14th pin and V reference negative at 15th pin. So depends the output voltage, the digital input we are giving, we are converting it to output voltage. That output reference voltage, how much output voltage we get, that depends on what we give to these reference pins. Okay, so this is what about the pins available on a DAC chip. Now let's see how this is interfaced, connected with the processor through 8255 peripheral interface device 8255. Okay, so here we can see this is the DAC chip. The digital input is connected to the port A pins of 8255. So port A we have to initialize here as output port. The digital data comes from the processor to port A. From port A this is given as input to the DAC chip. Okay, so here you can observe, here this is LSB and MSB. Here it is reverse of that. This will be MSB and this is LSB. Okay, then all these connections we know already. The 8255 data bus connected to the processor's system data bus D0 to D7, and 8-bit address A7 to A0 is decoded here for chip select and for the port A, port B, port C selections, and IO read and IO write bar connected to read and write of 8255. Okay, so here we see in this this is the digital input. Here this is the supply voltage given plus 5 volts to V plus the 13th pin. Then V reference positive. Here this is connected to the reference voltage is given here through the resistor R14. Here negative is connected to ground. Okay, then this is the 4th pin. At 4th pin I out, this is where we get the current output. This digital input equivalent current output we get here. Using this op amp configuration, this current is converted to its equivalent voltage at V out. So we get the digital voltage output, analog voltage output at V out, ranging from 0 to 10 volts. Again, this range also depends on the reference voltage which we apply. Okay, so this is the these are the connections, and the output voltage V naught we get here, it is equal to V reference by R14. The reference voltage which we give here by R14 into R naught into B1 by 2 plus B2 by 4. This is the formula. Like this is how the analog voltage output occurs following this. So B1, B2, B3, B4, these are the digital input bits. So it can be 1 or 0. Okay. So depending on that, we get the V0 output. So here 8 bits are there, 256 combinations. That means your voltage, output voltage is, we get it in 0 to 10 volts if we say. So 0 input digital data will give the output voltage as 0. And FF input digital data, we should get the output as maximum approximately 10 volts output. Okay, so adjust this V reference R14 and R0 so that V0 with all digit inputs at high level, that means all bits, digital input bits at high level 111 is equal to the maximum output voltage 10 volts. Okay, so we need to design like find R14, R0 and V reference we should apply in such a way that we get the output at output when input digital data is all ones, output must be equal to 10 volts. Okay, so this is the hardware configuration, how we connect DAC to the processor through 8255, and we have used here port A as the output port to give the digital input to DAC chip. Okay, now let's see how we can program this 8255 to get a particular DAC output. What are the applications of this D2A converter are? Like they have many applications like in compact disc audio players. So D2A converter is used to convert the binary data read from the disk to analog audio signals. Even in speech synthesizer ICs contain D2A converters to convert stored binary data for words into analog audio signals. So these are some of the applications of D2A converter. For us just to see like how we can program this and get a required analog output, we can generate any waveform like triangular waveform or sawtooth waveform or square wave using this DAC by writing a proper program for that. Okay, so for example, let us write a program to generate a triangular waveform. Okay, let us generate a program. Let us write a program to generate a triangular waveform. Okay, so triangular waveform means the output must be like this. So here the input, what we need to do to generate this triangular waveform is first give initialize the digital input to 0 0, gradually increment this 0 0 from 0 0 to till FF. Once it reaches FF, then again decrement continuously till it reaches 0. Once it reaches 0, again increment to FF and so on to generate a triangular waveform. Now let's see how we can write a program for this to get a triangular waveform. Now let's first write the control word. This is more important to initialize the port A as output port, because we have connected port A to the input of DAC. From here is from where we are this DAC is getting the digital data. So port A must be initialized as output port in simple IO mode. So the control word will be IO mode, group A in mode 0, port A as output port. All the other ports like we can say don't cares. We can take it as input or output. We are not using the other port pins. Okay, here important is this port A, it must be initialized as output port. So the control word will be ATH. Okay, for the hardware connection shown here, the address of port A will be FCH. Port B address is FDH. Port C, it is FEH, and control word register address is FFH. These are the addresses of the ports of 8255. Now to initialize this 8255 port A as output port, first write this control word ATH to AL and write this to control word register. So AL to control word register address is FFH. Okay, now it is initialized. Port A is initialized as output port in IO mode. Now initialize for triangular wave, initialize first take 0 0 and send it to port A. Okay, first, so move AL with 0 0 H, initialize it with 0 0 H. Now send this one 0 0 H to port A. That means you are giving this 0 0 input to DAC, digital to analog converter. Okay, so port A address is FCH. Now this 0 0 will be converted to its analog equivalent, that is 0 volts at the output. Now increment this. Okay, out this. Yeah, one more point is, like, if we continuously increment this and send to the output, because the processor speed is more, like we give 8 megahertz or 10 megahertz clock to the processor, this the waveform which we get at the output, the conversion 0 0 to FF increment and conversion to analog, it takes very small time, so that like it will not be visible. The waveform will be of very smaller amplitude that we cannot make out. So let us introduce some delay so that we can see the output triangular waveform. So this output we can view by connecting this output terminal on CRO to get the triangular waveform. Okay, so call a delay, small delay program, so that we get some small duration after each increment. Okay, so increment AL. Now AL becomes 0 1. Now compare this AL with FF. Compare this AL with FF. That is, we are finding out whether this has reached the maximum value, digital value, that is FF. If it is not FF, then again 0 1 it became, it is not equal to FF. So again send this to output port A. Okay, so compare this. If it is not equal or not 0, then repeat. So this repeat 1 will come where? Out. Okay, so the program control will come here, again send us data to port A, call delay, increment again AL, let's suppose it become 2, compare. If it is not equal to the maximum value, then again repeat. So this is repeated how many times? Till FF, till the AL contents become FF. Once AL contents become FF, it comes out of the loop. Now you send this also, that means FF also to port A, call delay. A small delay is given here. Now start, once it reaches FF, the maximum value, now The triangular wave is in such a way like it must be decremented to 0 0. So decrement AL contents. So from FF it becomes now FE. Okay. Then compare this AL contents with till where it should be decremented till it becomes 0 0 H. So 0 0 H. Jump on no 0. If it is not equal to 0, to repeat. Two. Okay. So this is sent to port A. This is sent to port A. Again decremented. If it is not equal to 0, again repeat. So this will be in this loop till it becomes 0. Once it becomes 0, then again, like after it becomes 0, again it should be incremented to FF. It is a continuous triangular waveform. Okay. So again, once it reaches 0, again go to the start of the program to repeat the process. To repeat 1. Okay. So again it comes here. The 0 0, it is uh, sent to the port A, incremented and compared. Okay. So this process repeats continuously. This is in a continuous loop. Okay. So when this program is written and gets executed, at the output of DAC, like V out, you can observe this can be connected to a CRO and observe a triangular waveform occurring. Okay, we get a triangular waveform at the output. We can write a delay procedure here. I have explained you how to calculate the delay. There is a one video on software delay calculation, software delay, so you can watch that to get to understand how this delay procedure can be written. So move CX with some count. This count is to be calculated if we want a particular delay. If I say 1 millisecond delay, then for that 1 millisecond you have to calculate this count. Okay, so this is return. So here a count is loaded. When loop instruction gets executed, this count is decremented and compared. If it is not 0, again it is in the same loop. Again, it executes this particular instruction how many number of times? 3f number of times. So that is the delay which you are giving in between each one of these increments or decrements. Okay, so this is the program. So if you want a sawtooth waveform, this is a triangular waveform. Let us suppose you want a sawtooth waveform at the output if it is asked. Then a small change in the program you can do. This is the sawtooth waveform, isn't it? So from 0 0 to FF. Once it reaches FF, it should be loaded with 0 0 again. Then increment this till FF. Then load once it reaches FF, it should be loaded with 0 0. So should make changes in the program accordingly so that you get a sawtooth waveform. Okay, in the same way you can generate a square wave by giving delay. So square wave of how much delay? So the delay program you should write here for how much delay it should be in this level and drop to the like 0 0 to FF. It should stay in FF till how much time? So the delay you must give. After that delay, this must be dropped to 0 0, and in when the output is 0 0, how much delay you need to give? Okay, accordingly you should write the program. So if a frequency is also mentioned, then you should calculate properly the timings, delays and all, so that you get that particular frequency. Okay, so this is about DAC interfacing with 8255 to the processor through 8255.